Hi everyone. In this experiment, we're going to be measuring phosphate in Duck Pond and Boone Creek samples using colorimetry, external calibration, and standard addition, and we're following another standard method. But there is a lot to unpack here, so maybe we could begin by talking about the colorimetry part of the experiment. So let's imagine that in this Erlenmeyer, we have a solution and it contains phosphate. Maybe you're imagining a sample, maybe you're imagining a standard, whatever you want is fine. What we're going to do in this experiment is we're going to treat all of our standards and our samples with a molybdate reagent that binds to phosphate and tin-2 chloride that reduces it to this beautiful molybdenum blue complex. And the nice thing about the molybdenum blue is that it absorbs radiation at 690 nanometers, which is in the visible portion of the electromagnetic spectrum. Lambda max here means that this is the wavelength of maximum absorbance. So how are we going to measure the ability of this molybdenum blue to absorb radiation? We're just going to use a simple spectrophotometer, or a Spec 20 for short. You'll put all of your standards and samples in a cuvette. This is a cuvette here. And inside of this Spec 20, there is a light source that gives off many wavelengths of radiation. There's also a wavelength selector that allows us to pick the wavelength of our choice, and for us, that's 690 nanometers. Our samples are going to absorb that radiation and get converted into an electrical signal, which will be displayed right here. So that was the colorimetry part. I wonder if you're thinking what I'm thinking. Are you thinking that the higher the concentration of phosphate, the more intense this color, the higher the absorbance? If you were thinking that, you'd be correct. What you're looking at here are solutions with increasing phosphate concentrations. You can see that the intensity of that blue color increases, and you can see that as phosphate increases, so does the absorbance. So let me define a few terms for you. If the radiation striking our sample cuvette has some initial intensity or power called P naught, and the intensity of radiation leaving our sample has some intensity or power or called P, we can define transmittance T as the ratio of P over P naught. And that allows us to define absorbance A as the negative log of the transmittance. And these equations are important, but the more important equation is Beer's law. Beer's law states that absorbance is equal to epsilon times B times C. So A is absorbance, C is concentration. So even if you don't know what epsilon and B are, you can tell by looking at this equation that absorbance is proportional to concentration. If you plot one against the other, you'll get a straight line whose slope is equal to epsilon times B. But let's talk about epsilon and B, and let's talk about B. B is the path length that the light travels through our sample. So looking at our diagram, this distance would be B. That would be the path length. The final variable we haven't defined yet, epsilon, is the so-called molar absorptivity. Older books called that the extinction coefficient, and it just describes the ability of a compound to absorb radiation. But the main thing about Beer's law is it just says that absorbance and concentration are proportional. There's a nice linear relationship. So let's talk about external calibration. In the external calibration method, you're going to have a series of 50 millivol flasks, and the procedure tells you to make standards that range in concentration from 0.5 ppm to 5 ppm. You can choose whatever concentrations you want here. Maybe I would choose 1, 2, and 3. And the procedure also says that you have a 100 ppm phosphate stock solution that you can use to prepare all of these standards. So what you want to do before you come to lab is figure out how many mils of the stock solution need to be diluted to 50 mils such that you get all of these concentrations. In other words, you're going to want to use C1V1 equals C2V2. In other words, if C1 is that stock solution, how many mils do I need in order to prepare, let's say, the 5 ppm, and I want 50 mils of it? So you'll have to solve for V1 for all 5 of these standards. But once you add the stock solution to each of your flasks, you'll dilute each one to the mark using deionized water, and then you'll transfer each standard to Erlenmeyer's, and then you'll treat each Erlenmeyer with the molybdate and that tin-2 chloride, and then each of your standards will turn an increasing shade of blue. And then you'll make your calibration curve. You'll measure the absorbance of all of these standards. So this is your 0.5, your 1, your 2, your 3, and your 5. Hopefully you'll get a nice straight line. And then you'll take your Duck Pond and your Boone Creek samples. You'll add 50 mils of each to these Erlenmeyers, and again, you'll treat these with molybdate and tin-2 chloride, and if there's phosphate in Duck Pond and Boone Creek, they're going to turn blue. And then you'll measure the absorbance of Duck Pond and Boone Creek, and you'll use your best fit line to find concentration. So external calibration is fine when the standards have the same matrix as the samples. Now, what do I mean by matrix? The sample matrix is everything in the sample except for the analyte. So what would the sample matrix of Duck Pond and Boone Creek be? It's mainly water, but we know it has some hardness, we know it has some alkalinity, and it's probably got a lot of other stuff. So can we really be sure that the samples and the standards have the same matrix? Let me interrupt the video and give you an extreme example of when the sample and the standards don't have the same matrix. I've prepared these phosphate standards in deionized water. An external calibration is fine when the sample matrix is also largely deionized water. So again, external calibration is fine when the standards and the sample have the same matrix. But what if my sample has a different matrix? What if I have the delicious sample of chocolate milk? Do you really think that if I add molybdate and tin 2 chloride to this delicious chocolate milk sample, it's going to turn blue? Clearly, this sample has a different matrix than the standards. So what do we do about this? So what we're looking at here is a calibration curve of phosphate prepared in a very clean matrix, in a matrix of deionized water. But what if I could somehow prepare a set of standards in a matrix of chocolate milk? How would that matrix affect my ability to measure the absorbance? So in a matrix of chocolate milk, would you expect the absorbance to be lower or higher compared to this point here, which was prepared in that very clean matrix of deionized water? I think we're going to have a hard time measuring phosphate in chocolate milk. I think all of our absorbances are going to be lower compared to that deionized water. So this red line represents phosphate in a matrix of chocolate milk. So what if I'm doing this experiment and I prepared my standards in deionized water, but now I have my chocolate milk sample and I measure the absorbance and I go over here and I use this calibration curve prepared in a different matrix, and this is the concentration that I get, when really I should have used this line because it has the same matrix as the sample. So do you see what's happening? This is my actual concentration, and look what I've done. I've underestimated the concentration because I've used the wrong line. So how can we possibly account for these matrix effects? Well, we can use the standard addition method of calibration. Believe it or not, the sample, in this case Duck Pond or Boone Creek, is going to be added to every single standard. So here you're going to get a series of 50 millivol flasks. You are going to add 10 milliliters of either Duck Pond or Boone Creek to each one of your flasks, and then you're going to start adding phosphate. The first standard always gets 0 ppm phosphate. The next one gets 0.5 ppm, then 1 ppm, then 2 ppm, and then 5 ppm phosphate added. You'll dilute to the mark with deionized water. You'll transfer all of these to Erlenmeyer's. You'll add the molybdate, the tin 2 chloride. They'll all turn a nice shade of blue, and then you'll measure the absorbance. And now we have to think about what to plot on the calibration curve. So the y-axis is still going to be absorbance, but the x-axis is going to be the concentration of phosphate added. And look at this first standard. We've added 0 ppm phosphate. That is going to be the first point on our calibration curve. But notice that this standard contains 10 milliliters of either Duck Pond or Boone Creek. So if the sample contains phosphate, we're going to get a signal. And with increasing concentrations of phosphate, that signal should increase. And hopefully we get a nice straight line. So what do we do next? The next thing we have to do is find the x-intercept. So we're going to extrapolate our best fit line, and we're going to find the x-intercept of our calibration curve. And that equals the concentration of phosphate in this standard right here. I'm going to call that standard 1. And to be very clear, that's this standard right here. And remember, we didn't add any phosphate. All this solution is duck pond that got diluted. So this also equals the concentration of phosphate in the diluted Duck Pond or Boone Creek sample. Well, that's important, but really, who cares? The customer doesn't want to know the concentration of phosphate in the diluted sample. The customer wants to know the concentration of phosphate in this original sample. So what you're going to have to do is you use C1 V1 equals C2 V2. So if C1 is the concentration of the dilute sample, V1 would be 50 milliliters, right? Because that's how much you had. You had 50 milliliters. C2 is the concentration in the original sample, and V2 would be this volume. That's the volume of the original sample. So C2 is going to be C1 times 50 divided by 10. So you're going to take your x-intercept, you're going to take that x-intercept, which is C1 here, and multiply by 5. That'll give you the concentration in the original sample. Don't forget about this dilution factor for next time. So some reminders, try to do all of your calculations before lab. You may need very small volumes of the stock solutions, so you can use micropipettes if needed, and I'll show you how to use these next time when we meet in person. Mix all your solutions well, and if possible, try to plot your calibration curves before you leave. And the reason I suggest that is for the standard edition. In the past, we've gotten calibration curves that have looked like this. Not all the times, but sometimes. Remember, in standard edition, our first point is 0 ppm added, and there could be a signal there. In the past, what has happened is as we've increased phosphate, we kind of reach a plateau. And you don't want to observe that. So I would rather find out during lab if this is happening instead of after lab. So try to plot your cal curves before you leave. And in terms of safety, the molybdate is corrosive, so I would recommend wearing gloves, and you will be wearing goggles throughout the entire experiment. Put all of your liquid waste into the liquid waste container. Nothing goes down the drain. You will work in pairs. For the external calibration, you'll do both Duck Pond and Boone Creek. For the standard edition, You don't have to run both. You do either Duck Pond or Boone Creek. I'll make those assignments during lab. So that's it. I hope you enjoy the experiment. Thanks for listening. If you want to learn a little bit more about the Spec 20, you can continue to listen. I have one extra slide to show you. If not, you can just stop the video. So here is the inside of a Spec 20. This is our light source or our lamp. The sample cuvette goes right here. This whole region is the wavelength selector. So what happens is light leaves the lamp and it strikes this mirror, strikes this mirror, it strikes this diffraction grating, and this is where the radiation is separated into its individual wavelengths, and then it goes through this exit slit where it strikes the cuvette, and that's where absorption occurs. And back here, this is the device that converts these photons into an electrical signal. So just in case you were interested in learning more about the Spec 20, thanks for listening, and again, enjoy the experiment.